Good morning. Good morning. Let's see. What am I gonna do? What am I gonna do today? I'm gonna do something, right? I'm gonna do some work. So I'm gonna keep working on what we have been working on, which is the flow field data for our water in our game. So I was thinking about stuff last night while I was asleep, and I realized that the reason that some of the blur stuff was, the reason some of our shore detection was screwed up was because I was blurring the shore texture a bit, and let's see, we got calculate path, and that's our A-star stuff. Is this the map utils for all this stuff? Do we do the blurring here for the shore detect? Space is shore, fill colors. Yeah, so I think it's the math in the physics utils. So we go to the physics utils. I have this blur on. Where is it? God, where the hell? It's like call fill height array, and we've got the output distance output. Yeah, so we've got our blur radius, which is passed in here. What we want to do is if we're blurring our distance, our shore distance texture, which is a pre-computed distance to shore, by everything around it, but we shouldn't be blurring it if it's already 0. So basically what I should be doing here is if added weight equals 0, I guess if it's greater than 0 for this value, then we should blur. Otherwise we should not. Alright, so that should fix one problem that we were having. Let's take a look at it. So if the added weight is greater than 0, then we blur. Otherwise, we're just going to leave it as black. So what that should do is, because when we're blurring our zeros with non-zeros, which were the red, we were basically instead of blurring the shore out nicely, we're basically blurring it so that what was detected as shore was being written as not being shore, which would make it so anything close to the shore would we'd be able to penetrate that with our particles, and our pathfinding would do weird things with our particles for discovering our flow field. And I want to rerun that and see what that effect has, because I was seeing some weird thing around rocks where I was expecting like particles to not go under some rocks, but they were, and I'm like, what? Why is that? That's shore, right? That's not water, that's ground. And I thought it was because of some like imprecision in the texture or something, but I'm pretty sure it's the blur algorithm. So this is our texture right here. And this is the blur texture I'm talking about. All the black here is detected as shore, and I think we've blurred our our shore too much, so I need to recalculate this real quick. Good morning, Karakan. Hopefully things are going well for you. So let's see, we're not blurring our shore anymore, so this is what our blurred texture looks like. Interesting, it's all chopped up, which is kind of what you'd that's not really what I would expect. I'd expect it to be a lot more blurry. Well, let's do some ticks. And see if we see any differences in how the flow field was acting. Well, no real differences that I'm seeing. Everything appears to be doing kind of what it already was. Which is good, you know. Everything was already working, but we shouldn't have any odd bits going on. Yeah, we've got this particle here traveling away properly. I'm not seeing any particles penetrate the rocks like they were. Like, what was happening was we were seeing particles come through here under these rocks beforehand, and I'm not seeing that anymore at all. Alright, so before we start doing other things with our flow simulation, other than just cleaning stuff up, like we need to make our colliders for our outputs actually be squares, and so these particles over here will actually just head over in that direction as opposed to what they're doing. Like we need to make this emitter be an oval, and this be a circle, drain over here. Looking at this simulation, are there any other things that we want to look at first? Like this area, these particles are going to be going in this direction. We're just going to have this like motion of water which is going into the rocks here, when what we would expect is the motion would actually come around and drain over here. So the question is, should we add some more pathfinding stuff around in this water area in order to get more particles moving properly? As in, or does it even matter? Well, let's throw a bunch of ticks on this thing real quick and do that. So I think it was 75 that we were using yesterday, which worked real well. So we'll just do 75 ticks on it and see what it looks like. And it takes a little bit to compute all this. So it'll do its thing real quick here. So that's 75 ticks on it. And yeah, we're seeing some decent stuff going on here. And it's okay if like we've got some weird motion around here. We're not like, if this was a real simulation, we'd have a lot more crazy stuff going on. We're just trying to get something that kind of looks right. Like, this is a complex, really stupid scene, to be honest. Like, we don't need a big snaking pathway and all this ridiculousness in our game. We're just trying to make sure it doesn't like completely break down and look like complete garbage town. Just a little bit like garbage town. That's all we care about. Alright, so I need to write down some tasks for me to do today. So I think we need to allow water particles to exit on edge nodes of map. So like right here, we get to the edge of this thing. Like, should we have actual drains to allow the particles to fall off the world, or whatever? Also, should we have any discovery of a drain? Like if we had these particles actually discover places that they could disappear into, we could have them go towards them if they're close enough. Alright, so we should have water particles detect close drains and head towards them. I'll have to think about how to actually do that. We need to actually detect the inputs / outputs for water in the scene. So we're going to need to, as a water object here, this big rectangle, it's going to need to detect the water boxes, like this water box that we have over here. And we also want to detect the waterfall itself. We should have like a little piece of geometry here that would spawn water. We'd want like an input, an outflow up here for the waterfall and an inflow down there. It should just, if we added another body of water up here, we just automatically find it in the scene and be like, oh, there's a water input, and like how big is it, etc. So what we'll want to do is add water input / outputs for waterfalls, and then we're also going to want to allow them to control the flow rate. Some sort of thing like that we can mess around with. And that should allow our simulation here to start working alright. So some other things here. I want to figure out how to access the flow field data at runtime. So we've got it stored in a texture, so we can access the flow field data from inside our material. Like when we actually draw the water, I'll be able to, turn this flow field data into stuff. Like I can read the distance map texture here, right? Like I can read that in a material. Obviously, we're reading it here, just showing it, having it show up. There's something wrong with this, isn't there? Because I would expect this little texture here to have kind of this black outline, but it doesn't. Something's wrong. So let's see, we've got our added weight, which is we're going to take our distance buffer to begin with, which has no blurring on it. Well, let's open that blueprint real quick, change the shore blur radius. The shore blur is controlled down here, so let's just put the shore blur at 0 and see what that texture looks like. So with the 0 it looks like this. So maybe we don't want to blur it as much, and that's what we want to... Wow, this looks a lot better just like that. Well, let's construct our static flow field and tick it and see if that has any sort of... If this actually does a better job. Or maybe we actually should only blur this a little bit. So we gotta calculate everything all over again here. So it'll be just a little bit. It'll be interesting to see exactly what this thing does now that we have a different little bit on it. Yeah, that actually found the channel a lot better, because we put a heuristic on avoiding the shore, and yeah, that did a lot better job of like staying off these rocks. So I guess our shore blur should be much lower. We'll put a default of, let's just say 4. Let's try 4 for this and change our tick method here. Let's change the tick down back to 1. So let's construct that height map so we get the updated distance. So that's with a blur of 4. Let's try a blur of 8. 8's looking pretty reasonable. Yeah, well, maybe not. Maybe 4 is better. I was trapped in a post office. Oh no. Starting to really take shape. Well, this was the previous work that we're then building this flow field off of. But yeah, it's starting to take shape. It's, you know, it's a slow process getting a lot of this stuff together because, you know, it's not like I'm an expert on fluid dynamics or anything like that. In fact, I'm very much the opposite. But we can see with the blur fix in there, our initial paths are much more reasonable looking. So another thing that we could think about would be perhaps trying to have some sort of look up into our path to see which direction we should be going. So it's a learning curve? Yeah, this is the learning curve right now. And what I'm trying to do is I'm trying to get this simulation to where I really want it, and if there's anything else that I can do before I kind of leave it for a little while. So what we kind of want is, if our particles tried to follow their assigned paths a little bit more, like right now we just like spawn the particle out and it tries to go to the exit. So we see all these particles here slam against these rocks. And what that's going to do is it's going to make a whole, you know, if something was following this water around, this water motion is actually going to be more towards into these rocks than it is going to be where it probably should be going. So we might want to have some way to look up which direction we should be going based on our position. So how would we do that? Because like if I'm a particle and I'm right here, what I would do is I really want a pre-computed grid for this, because if every particle has to like go search around for like a little guide layer, that's stupid. If we kept our initial guide position and said like, oh, I should be going this direction, then all these particles are going to get kind of like slammed into these rocks over here, and then they're going to kind of stay there. Well, we can just go ahead and try an initial position. That might actually be okay. So why don't we try that? Let's just save everything here. So next tasks, those current tasks, have particles remember their starting direction and try to go in that direction first. Something like that. Alright, so we go to our map utils. Yeah, why don't we just clean up some of these functions we're not using? It didn't work. I mean, we don't use them. Same. We didn't use them because they didn't work. Alright, so when we spawn a particle, we're going to need more values on here. So that's the map. Okay, so we want our initial effector 2D initial velocity, initial direction. Let's just call it that. Alright, so we have try spawn particle on a specific location. You have very strange music. I'm just using the the adventures playlist, which was kind of whitelisted by Twitch for streamers on Spotify, so it's not really even music that I usually listen to. It's just music I can listen to without getting copyright strikes on things. Because it's kind of annoying trying to get something that you can listen to that you can actually have on Twitch, and you can also post to YouTube without like everything going straight to hell. Without, doing like a whole bunch of work or something else. So let's see. We need to grab the current node on the path. So this is our node, and so I guess try spawn particle should also take an initial direction. Let's just have dx and dy. So we'll say dx is 0 and dy equals 0. Or how about effector 2d initial dir? Can we set references just inline like this? I guess I'll find out. So I guess we're going to need to add this to our flow path node. So our flow path node direction vector is going to be something that we need to actually create when we're finished calculating our path. So I'm going to avoid a bunch of normalizations all over the place by calculating this when we actually finish our path. Alright, so we're going to call calculate path. Right, so calculate path, when we actually find the path is down here. Alright, so our pathfinding stuff is, I believe, reversed. Like, so our direction is going to be, so we need to calculate our directions based on our nodes. The list of nodes is reversed. So direction is to the node behind us. Alright, so we're going to want like for int32, I guess we can just say I equals path.mnum, path.m, path.num, -1, I is greater than or equal to 0, minus I. So let's see. Let's just say greater than or equal to 1. We need to calculate the path direction, so that's going to be, let's just say cur equals path.mpath sub I, and next is path.inPath sub I minus 1, because we are going to 1, this will never error. So our f vector, so I'm going to say m direction equals what? Next.mx minus curve.mx. So curve.m direction equals this for x and y. And curve.m direction dot normalize. So that'll compute all of our direction values. So we'll get our initial directions, and inside of our tick for our particle, we can then add a weight towards that direction. So we're going to want here a float initial direction weight. Let's just say it's going to be 1.0f or something. And we're going to say plus this m, what is it, initial direction multiplied by initial direction weight. And let's see what that does. Let's see if any of our let's see if our particles will basically take the initial direction that they were going to go in. If they're a random particle, they're not going to have any dead reckoning, and this should make it so particles flow in the direction that they initially were going. The problem is, in tight turns, we might see a whole bunch of really bad behavior going on. But let's take a look at it, and we'll see if some of our other heuristics, like the initial, like the avoid weights and the goal weights and everything else, kind of work. And of course, we don't really need we're actually going to have to set this direction, aren't we? Yeah. So we'll see how this works. Alright. It looks like, yeah, we can use const vector references, and actually initialize them to something. That's cool. Well, that's interesting. We're seeing a lot more motion of particles kind of coming off and over. Like we're actually seeing a little bit of spin off on these things. And we're seeing a lot of, actually a lot more particles getting stuck into stuff here because it's the momentum is twice as high for these sorts of particles. They're not avoiding each other nearly as much as they were. Well, I don't think the weight's correct at all. Let's lower it to like 0.25. So we're just playing around with a lot of the values. Oh yeah, I guess other things we want to do is parameterize all the things for particle flow field generation. So we can change all these things without having to recompile our code. So there might be different flow fields where we don't care about like avoidance or whatever, or maybe we care a lot more about avoidance. You'll put down your water and then you can mess with like the particle generation stuff. And then you can kind of tick it and see what we want. And we'll do that right after we kind of solidify the basic concept. Yeah, it's looking alright. I know it's kind of just watching a whole bunch of little pixels get made and like ticking them and seeing what they do is kind of in and of itself a little interesting thing to mess around with. Oh, that is really actually interesting. So the heuristic for our pathfinding is making us avoid this. Let's see what the particles do. Well, the interesting thing is we have how you kind of look at this is the purple particles are particles that were able to move more. The blue particles are particles that have not been able to move as much. So these particles are fast-moving particles, and you can kind of tell where they came from. So because of our distance heuristic is actually working, we're now going to have like the main flow of water come around here, but then we'd have like a high flow area here as well, which is kind of what we want. Alright, I think that's working pretty well. So what we want to do is I think we want to parameterize these things, and then we'll start working on the rest of this. So let's parameterize the inputs to our simulation for the particles so we can actually affect all of that generation stuff from inside of our blueprint. So what are we going to need? We're going to need, let me pull up the code here. Okay, so we're going to need a void weight. This is a float. We are going to need a goal weight. Give me a shore weight. I guess I should call this a shore avoid weight. And this will be a particle avoid weight. We have initial direction weight. We're going to want a shore avoid distance check. This is going to be an integer. Shore avoid distance. Yeah, that should be it. We're going to want an avoid radius, so we'll duplicate that. We're going to want a particle avoid distance. Let's see. We're going to want the history. Particle history. Length. We're going to want a particle life min and a particle life max. We're going to need a random particle percent. Is that going to be a percent, or should we just have it be a random particle amount? Random particle number. Let's see, the computer's kind of chugging a little bit right now. Let me just take a look at what's actually taking up any time. Looks like it's just OBS. OBS is a frickin' hug. Alright, are there any other pieces of data that we need parameterized? It looks about right. Why don't we have a tick number? Alright, so I'm going to throw all this stuff into a category. This is going to be a particle sim category. And yeah, we're just going through, doing our due diligence here, because we've actually got our working stuff. So, you know, let's kind of polish it up a little bit. So, change this. This affects how strongly particles avoid each other. The particle avoid weight is by default right now 1. Let's have it go from 0 to, you know, like 10. Alright, goal weight. This is how strongly a particle tries to head toward its outflow node. So it's going to go from 0 to 10, and it's going to be 1 to start with. Alright, short avoid wave. This is how strongly a particle avoids shore, that is close. Alright, so slider range should go from 0 to 10, and the initial weight is 3. The initial direction weight. This is how strongly a particle attempts to follow the path along, to follow its initial direction. Let's just say that. It's probably less confusing than anything else. So we'll do 0 to 10 and default to 0.25. And I'm writing all these notes basically for myself and for Adam, so I'm trying to put some language in there, so if Adam read it, you'd actually go, oh, what the hell does that mean? So hopefully make it a little less technical. A little bit more intuitive. Alright, shore avoid distance. This is the distance at which we try to start avoiding shore. Alright, so that shore avoid distance is 10 at the moment. So we're going to go from maybe 0 to 32, with an initial value of 10. Alright, particle avoid distance. This is the distance at which we start avoiding other particles. Right now, what is this? Avoid radius is 3. Let's go from 0 to 10, and we'll just have it start off at 3. Particle history length. This is how long a particle remembers its position history. So we'll go from 0 to 20 with a default value, I believe, of 10 is what I had. Alright, so particle life min, the minimum lifetime of a particle before the end. Slider range will be from 0 to like 200. And we're going to default it at 75. Particle life max. This is the maximum lifetime for a particle. Slider range from, what did I put on this one? 0 to 200. Let's just do the same thing, 0 to 200. And default to 250. Alright, so let's see, random particle number is like 100 or whatever. So this is how many random particles are created each frame, each tick. So let's go from 0 to like 512 and a default value of 100. Tick number. This is the number of ticks when you click the tick button. So it should be from 0 to, let's just put 250. Current tick number at 50. Alright, let's save that out. So we're going to need to be able to use all these parameters we just created. So does it calculate paths? Yeah, it's just calculate paths is our thing here. So we're going to need to pass everything in. Alright, so I'll throw this on my other monitor. Alright, so we need to take a whole bunch of variables here. So I'll have float, particle void weight, float goal weight, float shore avoid weight, float initial direction weight, float shore avoid, so that's an int 32. Particle avoid distance, that's int 32. Particle history, int 32 particle life min, int 32 particle life max, int 32 random particle number, and 32 tick num. Alright, tick num we don't need. Let's just organize this a small bit. This is where Sinacron would be like, Jesus Christ, dude, just get, just set it so that it automatically formats. I'd be like, nah, I'm not about that. Not about that auto format. It's kind of one of the things when I'm working. If your typing speed is what's holding you back with your program, you're doing it wrong. Like, just straight up, your programming speed should be limited by the algorithm you're doing, and if it's taking a million years for you to type something out, it's probably that you need to slow down and think a little bit more about what you're doing. So I think what I'm going to do is I'm going to throw all these as variables on this class, and then I can just go reference them. Hello, the former CC. How are you doing today? I am just getting started, and I'm doing well. We're just working on this particle fluid stuff at the moment, trying to get our stuff rolling here. Glad to see something that's not a scripting language. What are you talking about? C++ is totally a scripting language. The only true languages are like assembly, right? Am I right? I mean, breakpoints are for chumps. I want to set the B register to 0x5 in order to actually have a debug breakpoint. Let's go back to the Game Boy Color. That was the highlight of programming forever. Alright, so we got all this stuff together. Let's see, do we have a constructor for this class? We do somewhere. Alright, so we have our reset function here, so instead of an initializer list, I'm just using a reset function because I don't care about anything. Oh, I thought C++ was trash. Yeah, C++ is kind of a trash language. I mean, it really is. Like large programs in C++ just always end up being a complete clusterfuck. Like, just look at like any game, just like everything goes to hell. Like, just look at like CryEngine or like Rise Son of Rome had like 11 component systems deep or something like that before it actually had any logic in the game. But the amazing part about C++ is that even though it always turns into a giant mountain of crap, it still works. You know, like, I think when I was at Amazon, they tell stories about how they wrote like everything initially in C++ forever, and they had to start instituting company-wide rules when you actually checked in. They got so unmanageable after like 10 years that they enforced this. It didn't matter what the feature was you're writing, you had to remove code from the code base to add any code to the code base. So, like, you would literally have people on your team who are just actively removing code from the code base, and that was their entire job, so that you could have other people actually add or update new features on the website. When you think about that, it just sounds absolutely insane. Like, Jesus. So I'm going to fill in these defaults here, just because I like to do that. They use Java now, so of course they don't have that problem. Oh man. Shore avoid distance, that was 10. Particle avoid distance was 3. Particle history was 10. Particle lifetime was 50. Particle lifetime max was 150. No, this was 150. Random particle number was 100. Alright, so we should start actually using these things. You're waiting. You're taking an online assessment for Amazon soon? Well, Amazon's not moving towards C# at any point. Though, you might have some luck with Twitch as Amazon owns Twitch, right? I believe a lot of Twitch's technology is built on C#. I know at least some of their client tech that they've got, they're working on C# projects. So, if you're waiting for C#, you might try to bug the Twitch people. The Amazon recruiting process is kind of a shit show, though, so you never really know who you're actually going to be able to interview for. I, though, have not used C# enough to really have a strong opinion either way. Pretty much all my coding experience, most of it, I'd say, if I was to characterize it, was about 60-70% Java and 30-40% C++ servers and games. Mainly, servers. Not too many games written in Java on the client side besides, Minecraft and Towns and the rest there. Kind of a child of Java and C++. Well,